Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is ASTM E1300-2024 glass design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They are both support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout this presentation. You can do so within the GoToWebinar dialog box as shown here. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So regarding the content over the next hour today, I do want to begin with a brief introduction to the glass design add-on available within our program RFEM 6. We'll then move on to our first example that you can see over here on the right-hand side, which is a simple laminated curved glass panel. We'll talk about the modeling and the loading. We'll run a quick analysis and we'll carry out the design according to the ASTM standard. For our second example, we'll move on to a facade wall. For this one, we do want to integrate the aluminum member design along with the glass panel design, also according to the ADM standards and ASTM. So let's turn now to a quick introduction to the glass design add-on. This particular add-on is seamlessly integrated within our FEA program RFEM 6. So RFEM provides the analysis of our structure, including the modeling and the loading, but when we want to carry out the design of these glass surfaces, we do need this particular add-on. This add-on also allows us to define monolithic or laminated thickness types, just as a fact that we are working on the insulated glass design as well. We'll cover this more towards the end of our presentation today. Now, within the RFEM 6 program, we do have access to our material library for glass materials and foils, but you can also create your own user-defined materials as well. We have the ability to specify the shear coupling behavior between the laminated glass layers as fully uncoupled or release, or fully coupled or rigid. We do utilize what we call the laminate theory to calculate the panel stiffness. So we consider all of the various layers within a laminated glass panel. We apply the laminate theory to come up with the stiffness matrix for the overall surface. So we'll see this in our example today. We can apply line, nodal, or surface support types to these glass panels. And when we carry out the analysis, we have the ability to drill in a little bit further into each individual layer to view information such as the tensile stresses. And finally, we have the ability now to apply the ASTM E1300, the latest 2024 design check. So in our previous version, RFEM 5, we carried out a general stress design for glass. We did not have the ASTM, so this is something new that's now available within RFEM 6. So we'll turn now to specifically the ASTM E1300 and how this is integrated within the program. So the first thing to note is that we can generate the load combinations automatically according to the ASCE 7, but it is required that when we enable this glass design add-on that we choose the ASCE 7 glass load combination generator. And the reason why this varies from the standard ASCE 7 is that for our various load cases, we now have enabled the load duration factor. So this is needed to carry out the strength design of our glass panels. Now, the IBC is also a little bit more clear about serviceability limits for glass or members that are supporting glass panels. So we are going to generate the load combinations for this type according to the IBC and section 1604.3 for our serviceability or deflection checks. And again, this will make more sense as we move through our examples today. So from the ASTM, we are going to calculate the max allowable tensile stress for each surface. And for this, we refer to table X6.1 and X6.2. Now, this is dependent on the glass type, the load duration that we talked about up here within the load combinations, and the probability of breakage. Now, I would recommend that you reference the ASTM in this particular section because there are some assumptions here that are made, such as a uniformly loaded glass plate, or there are some limitations with thickness and size in order to calculate these max allowable stresses. So if you don't fit into these particular criteria or recommendations, then you would want to use your engineering judgment if perhaps maybe a general stress design, which is code independent, would be better within the program. There is also an additional check for the max edge stress, and for this we refer to table X7.1. Now, this edge stress check is only carried out for load combinations that include a 3-second load duration, and also the probability of breakage must be less than 0.008. So in the program, we'll see how we specify for these laminate glass types the edge finishing, including clean cut, seamed, or polished, because that does play an influence here within this table on the total max edge stress that is allowed from the standard. Now, it should also be noted that if we do refer to this table, we do not have edge stress checks available for heat strengthened or tempered glass with clean cut edges. Okay, so we will turn now to RFEM for our first example. So when we do launch the main program RFEM 6, we will go ahead and give it a model name within the base data dialog box. The second tab that is shown here are all of the various add-ons that we have available. So more or less, you can create your own software package that's specific for your design needs. For this first example, we will take advantage of the Glass Design add-on. So under the third tab, this is where we can set our standards. The first one is the drop down to generate the load combinations automatically. And as mentioned in the PowerPoint, we do need to select the ASCE7 glass option here. The glass design dropdown, we now have the ASTM E1300, the latest 2024 standard. You'll also notice that you can choose a code independent stress design as well if you prefer. So once this information is input, we can click OK when we're brought here into the main program. So we have our graphical interface to work with here at the center window. We have our quick tools up at the top. Our navigator on the left will include our input data as well as our results, or we can work with the table options down here at the bottom. So we'll begin first by drawing a simple line element. And a line element can be found up here in our tools. So rather than a straight single line, I am going to choose an arc where I can define here the start and end nodes as well as the radius. So I'll snap here to the origin point. My second point is going to be 5 feet away in the Y direction. And then I want to either graphically select here what the radius is, or in this case, I'm going to reverse the orientation and to directly type in the radius into my dialog box. I hit enter and that line element is complete. So I right click on my mouse and I'm going to select this line element. We have the ability here to right click to extrude this line into a 2D surface. And I'm going to create my surface panel here that will be 8 feet in the vertical Z direction. I hit apply, I'll right click to exit out, and we have our surface shown here. Now it's currently displayed as red because we do not have a thickness or a material assigned to it. So we'll double click on this surface and we can assign here a new thickness type. We create the new thickness type within our dialog box, and under the drop-down is the option for glass composition. So if I did not enable the glass design add-on, I would not have this available option. Under the second tab, this is where we can begin to create these layers for our laminated glass. And we'll begin under this first row for the material, defining here a new material, which we can select directly from our library. Over on the left, we have our material type dropdown. that we can select glass, and we can further select the ASTM standard. So we have 3 different glass types available here, including a fully tempered glass material. I can click OK, and that information is brought into here. Now, if your glass material that you're using is not found in our library, what I would suggest is to choose one of the options as a template. And then we can always come down here to select user defined, and then we have the ability to modify the material properties directly. We can rename this material, but for today's example, I'll go ahead and use the material available to me within the library. The thickness type is going to be 0.25 inches for this first layer. And then the edge finishing. So you remember from the PowerPoint, we can go ahead and check those edge stresses, but we need to know what type of finish from this drop down. So we'll go ahead and select polished edges for layer number 1. Layer number 2, we will create a new material once again from our material library. And this time, instead of the material type set to glass, we're going to choose foil. Now we do have some code independent materials available such as PVC, or we can use our drop down here to select the ASTM again, and we do have the manufacturer Century Glass implemented here. So we can go ahead and select one of these products. I click OK, but once again, if you don't see your foil type, you can always turn on the user defined option here. So we import that in as our second layer, and we're going to set a thickness of 0.03 inches. Our third layer is going to be the same fully tempered glass. It's already available within the RFEM model. I don't need to redefine that material type, and the thickness will be 0.25 inches here. So a couple more things to note, that this is a very symmetric laminated glass composition. If it was not symmetric, let's say we had maybe a thicker or thinner layer 1 or layer number 3, we would want to pay careful attention here to the local z-axes shown and ensure that the local z-axes are oriented in the correct direction once we do assign this thickness. The other recommendation is that if we're continually working with these same laminated thicknesses, with these same layers, is to save this to your library. So you can save it as a template, you can give it a name, and this way for any future RFEM models, you don't have to keep redefining these layers, but just simply pull them open from your template. So once this information is defined, what you'll notice here is that our surface is no longer red. It's now assigned a color because we have a thickness and a material also assigned to it. Now over on the left in the navigator, we have our various folders available to us, and one of them is the types for glass design. So the program has automatically created a composition when I have defined this laminated glass. And this is going to be where we specify here the shear coupling behavior between the layers. And within this dropdown, we have fully coupled, which is a rigid coupling at the boundary edges, or uncoupled. So we'll go ahead and leave this as uncoupled for our example today. The third tab is the stiffness matrix. So as I mentioned in the PowerPoint, we are applying what we call the laminate theory to calculate the stiffness properties for the entire panel itself. So we're considering all 3 of those layers. We apply the laminate theory, we determine what the stiffness is, and this is what we're going to use in the analysis within the base program. So very powerful in the sense of being able to calculate all of these stiffness automatically. So once this information is complete, we will continue with the modeling workflow. And let's assume that we maybe have some type of handrail on this glass panel that we want to consider for loading purposes. So I'm going to take this bottom line here, highlight it, use my Move Copy tool to make a copy 3 feet in the vertical direction, and I click OK. So now this line element will be fully integrated within this curved surface. Now you'll notice a couple other symbols here for what we call surface cells. Those are not needed for today's example. So under our second tab within the navigator under special objects, we can go ahead and deactivate that graphically. Now, finally, we do need to support this panel. So I'm going to apply a new line support, which is available in my Quick Tools up here at the top. And for the bottom, I'm going to take advantage of this predefined support type, which is just a standard hinge support condition. So I go ahead and click OK, and I will select the bottom of the panel here, the bottom line. And for my top support, I'm going to once again go to a new line support, but this time I want to create my own definition type. So what you'll notice is that we have 6 degrees of freedom, 3 in translation, 3 in rotation, where we can fully fix or fully release this line support type. We have spring constants for partial fixity, or because RFEM is a nonlinear analysis program, we can assign a nonlinear behavior type to this support condition. Now for the top of my panel, I simply want to release the translation in the vertical direction, allowing that panel to move. But in the translation directions of X and Y, we'll go ahead and set a restraint there. We click OK, and then we can simply click at the top of this line element. So keep in mind too, you can always right click on these symbols and use our sliders to decrease or increase the size, just depending on your model type. So we'll now move on to loading. I'm going to access our load cases and combinations dialog box here. You'll remember that when we first started this example, we are going to generate the load combinations automatically according to the ASTE E7 Glas in particular. And this will automatically be done when this combination wizard is checked on. So if I prefer to manually create my load combinations, I would just want to uncheck this instead. Now, under the load cases, the program by default creates a self-weight load case. We'll go ahead and rename this one to dead with the action category set to dead load here. Notice self-weight is automatically accounted for, but the load duration is something that is unique to this ASCE 7 Glas option. So we made some assumptions here based on the various actions of what the load duration should be, but if you'd like to make changes to this, you can use this drop down for each load case. So we'll create a second load case here. This one is going to be live load with the action category of live. Notice the load duration is automatically updated. We have a third load case here for wind pressure. The action category will be set to wind. This is important to note that this load duration is set to 3 seconds. So this will come into play with those edge stresses that we check later on. I'll make a copy of this one and to simply rename to section. So now that the 4 load cases are defined here, you'll notice under the design situations, the program creates 3 design situations. The first 2 are referring to the ASCE 7. So the first is LRFD, or our factored load combination. So think of design situations as nothing more than grouping together these load combinations, and we use them later on within these add-ons. Now for LRFD, my factored load combinations, I'm actually not using those for today. So I can just completely turn it off here, or if I prefer, I could delete it altogether. The second design situation is ASD, or unfactored load combinations. We can click on the little info button here to see these directly from the ASCE 7. This will be used in the Glas design for our strength design. Now, finally, I mentioned in the PowerPoint, a little bit unique to the ASCE 7 Glas option is that the IBC is a little bit more clear about what limiting deflection should be for something like a glass panel or the members that are supporting glass panels. So therefore, we've created this third design situation, not related to the ASCE 7, but rather the IBC section 1604.3 to generate these load combinations from the IBC that will be used in the Glas design add-on for serviceability. So finally, under the load combinations, we can check out the individual load combinations listed. We see all of our ASD load combinations in red belonging to that second design situation. And then we see all of our IBC load combinations here belonging to that third design situation. Now you'll notice that the program by default for load combinations will carry out a second order analysis considering P delta effects, but large deformation or third order is also available within the program. So now that we have generated the load cases and the load combinations, we need to actually apply the loads to this structure. So we will select here the dead load from our dropdown. And I'm going to apply a new line load. And this is not to be confused with its neighbor here, a new member load. We don't have any members within this model, but a line load is applied to anything that is similar to a surface, for example. So the load direction is going to be in the vertical Z. The load magnitude here is going to be negative 0.1 kip per feet. And then I'm going to graphically select this top line here to apply this line load, and I click OK. So now we see that line load applied at the top under the dead load case. The next load case is live load. So this is going to be for our handrail. And for this particular loading, I'm going to right click on the line to turn on the local axis system of the line element itself. And this way I can go back to a new line load, but rather than applying the line based on the global XYZ coordinates, we're going to modify this to apply it to the local lowercase XYZ of the line element itself, and in particular in the local Y direction. So we select that here from our dropdown, and our magnitude is going to be negative 0.07 kip per feet. Line number 5 is already selected here. I click OK, and now we can see that live load applied to the handrail location. So we'll go ahead and turn off the local axis system of our line, and we'll move finally on to our wind loading. So for this one, I'm going to right click to turn on the local axis system of the surface this time, so we can see that displayed here. And I'm going to apply a new surface load. So we select the surface load dialog box, and again, very similar to the line element, I'm going to modify this to the local XYZ coordinates of the surface itself rather than the global XYZ. The load direction will be in the local lowercase z here, which is already selected. And our magnitude is going to be negative 0.03 kips per square foot. You can see surface number 1 is already assigned. I can click apply and next. So I still remain within this dialog box to continue making changes, but we can see that this load was applied in the background here as a wind pressure normal to the face of the surface. So this way I can toggle down to wind section and just make a quick modification here to my magnitude of 0.015 assigned to surface number 1, and I click OK, and now we have this additional section load shown here. So I have the ability to display these loads together based on the load combination, where the relevant load factor will also be displayed here graphically. So before we move forward with the calculation, a couple more things to take a look at. The first is going to be our mesh settings. So let me right click here to turn off the local axis system. And under our tool up here at the top, we have the ability to quickly generate the mesh. And by default, the mesh size is going to be 1.5 feet for any new model. And we can see that this is entirely too big for this panel. So within the same dropdown, we can access the mesh settings, and to modify this to a smaller value of 0.25 feet, I click OK and apply. And what you'll notice now is that we have a much smaller mesh generated, which looks much better for the FEA calculation. Okay, the final thing to talk about, and I'll go ahead and turn off the display of my mesh, it still exists, we're just turning it off graphically, is to double click on this surface. So you'll notice we have the design properties shown within this dialog box. This is telling the program that not only are we interested in the analysis within the base program, but we're further going to design it within the Glas design add-on. Now, when I turn this off, notice a couple tabs up here disappear. That's just simply telling the program I'm more interested in analysis than design. But of course, we want to carry out the design. So let's take a look at these additional tabs. The design configurations has everything to do with strength and serviceability specific to the ASTM. So looking at the default option definition here for strength design, you'll notice the first input has to do with the design stresses that we want to design for once we are within this add-on. And for this, I'm going to jump back to the PowerPoint to explain this in a bit more detail. I think that when we do carry out an analysis, it can be a bit confusing because there's so many stresses that are available to us within something like an FEA program. But when we are specifically looking at glass design, we typically look at tension stresses. Now, that's not to say that for specialty projects, we don't need to look at additional stresses. So for example, if we're designing a glass staircase, we may be interested in some of the additional stresses that are given to us. But referring now to the tension stresses, there are 4 of them available here. The first 2 have to do with the basic stresses. So these are related to the local axis system of the surface element itself, in particular the X and Y axes. And we have a nice picture shown here in the lower right that comes directly from our online manual, where we show how these normal stresses are related to this local X axis, so sigma X. The formula is also shown here. So it's based on the internal forces from the FEA analysis to determine this particular stress type. There's also normal stress in the Y direction, sigma Y, the relevant formula shown here. But then there are also the principal stresses. So these are related to the extreme values principal axes. So we're going to look at the max and min stresses. We're going to create these new axes, principal axes 1 and 2, and we come up with a different value here for principal stress sigma 1. So this is in the direction of principal axis 1. We see the formula given here. You'll notice that the variables are based on the basic stresses, not only the normal stresses, but also the shear stresses. We also have principal stress sigma 2 with the relevant formula. But by default, which we'll see in just a minute, the main stress that we will always design for is this principal stress sigma 1. But it's up to you as a user if you also want to select these additional tension stresses to design within the add-on as well. So going back to RFEM, as I mentioned, you'll notice this principal stress sigma 1 is automatically selected by default. The probability of breakage. So this is just a drop-down box here that we can select for this particular surface. And then we have the checkbox to consider the max allowable edge stress. Again, this was from the PowerPoint where we refer to section X7 from the ASTM. And it should be noted that this is only available for load combinations that include that 3-second load duration. So for our example today, that was our wind load. So any load combination that has wind in it, we will check the edge stress. For the other load combinations, we will not carry out this design check. You as a user also needs to specify here the distance from the surface border for these edge checks. Now the default here is a 2-inch border. So everywhere around the border lines of this surface in a 2-inch dimension, we will go ahead and carry out these edge stress checks if they fall within this category here. So once this information is defined, let us also take a look at the serviceability. This is just where we select here or input in here the limiting deflection ratio. So for simply supported glass panels, this is set as L over 175. For cantilevers, it's L over 50. These values come from the IBC, but you have the ability to override them here. And finally, the deflection tab. So this is where we can tell the program, is this panel supported at both ends or is it a cantilever? And this information is important because we need to know which limiting deflection ratio to refer back to. The displacement reference can be set either to absolute or to relative, and the default here is the undeformed system, or the absolute is what we'll refer to for this example. And finally, we need to give the reference length. So in our limiting deflection ratio, that L value, what should we refer to for this L length? Is it the maximum boundary line of the surface, the minimum, or can we manually define that here? For our example, we'll choose the maximum boundary line, which is the 8-foot height. Okay, so now that the configurations have been set, we will jump down to the table where we can select here the glass design add-on. And under this first tab, design situation. So remember, we created these design situations automatically, the program did, according to the ASTE E7 and the IBC. We have deactivated the LRFD. We're not using that today. But when I look at my ASD design situation, again, this is grouping together all of those unfactored load combinations. We want to assign this to the strength limit state within our dropdown. The serviceability or the IBC load combinations, we want to apply the serviceability limit state or those deflection checks. The second tab is the objects to design. We currently only have one surface, so we'll go ahead and design only that single surface, of course. So now we can run the calculation. So we either click on the calculation in the table, or we can go up here to calculate all. The program will cycle through all of our load combinations rather quickly and then apply the ASTM design checks, and we are now presented with our design ratio. So the first thing to note is that we can graphically turn on the display of the design ratio here, either the ratio envelope, so the max of both strength and serviceability, or we could turn on strength and serviceability individually here, again shown graphically. In table format, what we see here, if we jump to the design ratios by surface tab, is we have 4 different checks. Now, a couple of these are negligible, so meaning we don't really have any tension stresses, or maybe we don't have any deformations under this particular loading in this particular location. So we can use our filter to only look at our design checks greater than 0, and we're left with 2 simple design checks. The first is going to be the strength, where we are taking a look at that principal stress sigma 1. We see the design ratio shown here in table format. What else you have the ability to do is to expand here the design check details. Now, with the design check details, we can zoom in where we see the max stress from the analysis. You'll see also the allowable, and in this case, the edge stress, and ultimately how we are calculating this design ratio. Now, the edge stress is controlling for this entire panel at this particular location shown here with the red arrow. Additionally, we can display here the diagram of this glass panel. So this is a cross-section view looking at both of those glass layers and our foil layer, where in our dropdown, we can select the stress display, and we can view those normal stresses X and Y, or we can drop down to sigma 1, those principal stresses in the direction 1, as well as sigma 2 in the principal axes 2. We can also display here the shear stresses. We can add this as a picture to our printout report. We can add these formulas to our printout report as well. So everything is very transparent in ultimately how we're determining this strength design ratio. Now for our serviceability check, you'll notice that the red arrow moved up here. This is where our max deflection occurs. Again, we can view the design check details here. And you'll notice that we have the deflection from our analysis. We have our limiting deflection ratio that we've set for this panel, and the ultimate design ratio shown here at the bottom. Now, this is just the 2 controlling checks for the entire panel. If we want to jump to the design ratios by location, we will actually give you the design checks at every single mesh point within this panel. So if we jump here to an internal point instead, we are carrying out the tension stress for the principal stress sigma 1. But what should be different here is that we're no longer checking edge stresses. Rather, we're going to refer here to table X 6.1 or 6.2 for just the max allowable tensile stress instead, because we're not within that boundary here for the additional edge stress checks. Now, this was all the information specific to the ASTM glass design. We could back up a step to the static analysis within our navigator here. And what you'll notice is that over on the left-hand side, we can turn on information like the global deformation, and we could cycle through these different load combinations here just to see how our panel changes depending on the loading. We can also activate the support reactions graphically here. So the support reactions can be shown either within the graphical window or in table format. We see the results by line, and we're going to be able to see those support forces here where we can export out to Microsoft Excel at the click of a button or any other information that we're interested in table format. Now, we also might be interested in the stresses. So what's really cool with the glass composition is that you'll notice we have the ability here to select the particular layer, layer number 1, for example, and I can activate my principal stress, sigma 1, but I can view this on the top layer side. So we're currently looking at layer number 1, the top side. I can toggle this to layer number 2, the bottom side, and see the relevant principal stresses here. Or I could jump to that third glass layer and view the stresses at the top or at the bottom as well. So not only do we have the ability to view information for the panel as a whole, but we can really drill into each one of these layers to view the various stresses at the top, middle, or bottom side of the layer itself. Okay, so that will conclude our first example today. We want to now move on to our second example. So this might be a little bit more interesting because we want to integrate a full facade wall design. So I want to first begin in our standalone program, our section. Now, it's pretty common with something like a facade wall when we're integrating this with glass panels that we might have custom aluminum extrusions. So the powerful thing about RFEM is that we can carry out the design of these supporting members along with the glass. So that's what I want to show you today. So starting off in our section, this is our standalone where we can import in something like an AutoCAD file, and that's what I've done here. And we have the ability to calculate the cross-section properties of this pretty complex section. Now, I have a webinar devoted entirely to our section where I go into much more detail that we don't have time for today. But it's worth noting that once we define information like the parts, but also the elements, and you see these elements are somewhat highlighted here as I kind of click around. This information, once we calculate the cross-section properties, can be brought into RFEM where we can fully design these aluminum members according to the ADM. But the really unique and powerful thing is that we can also check local buckling according to Chapter B. I think that we're one of the only programs, or maybe there's another one out there, but as far as I know, I think we're one of the only programs that's able to also check the local buckling. So something important to remember here for these custom aluminum extrusions. But once we run the calculation, you'll notice that we are presented here with the section information like area, moment of inertia, shear area, and we would want to save these results in this file to a folder on our computer. So then we are going to go into RFEM. And for the sake of time, I have already modeled these aluminum members, and we'll get into that in just a minute to do just a quick overview. But before I do, let's visit the base data dialog box. So again, this would be the dialog box that pops up when you first create a model. And once again, we're going to take advantage of the glass design add-on. But I can also activate here the aluminum design add-on. So we can do the full analysis of these aluminum structures, but if we want to carry out the design checks according to the ADM, we do need to activate here this specific add-on. And under the standards, you can see the ADM 2020 is available, and then we'll go ahead and of course take advantage of the ASTM E1300. So now that this information is defined within the base data, we would want to draw all of our members. So when I would go to draw one of these custom aluminum extrusions as a member, I would probably go up here to draw a new single member. The member type would be set to a beam, and then I would define the cross section. Well, within our cross-section library for the supporting members with our glass panels, if they come directly from the ADM or the AISI or the AISC or whatever it may be, all of those standardized sections are available in the upper left-hand corner. Now we have some other parametric sections available. So for these, you would just input in the dimensions, the program calculates the section properties for you. But for anything more complex like that aluminum extrusion, we would want to import in from our section. So within our section, you can see here that I could right click in the projects folder to connect a folder that exists on my computer where I have saved this aluminum extrusion. And that's what I've done here. I've calculated the results. I've saved it to this particular folder. So we can bring that into RFEM. And what we would normally be presented with is the dialog box shown here where we get a nice rendered view. The material was already brought in from our section where I defined it, but I could always change it here to a different aluminum material from the library where we have all ADM materials available to us. So once we have imported in this section, it's also noted that when we draw members, the program assumes that each member that connects to the other one, the adjacent member, is fully fixed. So if we want to add in something like a moment release, we would just need to activate here the member hinges. And this is where we could define a new member hinge type, which you can see I've already done that in the program, where maybe we want to release the moment about the local Y and local Z axes. So we could apply this moment release if it is applicable to our members at both the member start and the member end. So I would go ahead and utilize my drawing grid here and draw all of my members. And again, I've already done so for the sake of time. What else is nice is I'll go ahead and turn on the display of only one of these members. Is that when you import in from our section, we do give you a nice rendered view of these extrusions. So there's no confusion here on the orientation of the member. There are other competitor programs out there that just kind of bring in a basic shape. Again, it's difficult to tell the orientation, but with our section integration, you can see here that AutoCAD, that DXF file was automatically brought in here for the accurate rendering. Okay, so we'll cancel out of this visibility mode. The other thing to know are just the nodal supports that are applied to our structure. So in our navigator over on the left under types for nodes, you'll see all the nodal support definition types as I click through them, just assigned to various nodes here within our facade wall. You will be able to download this model too later on, usually available by tomorrow. So if you wanted to kind of explore this model in a bit more detail than what we have time for today, again, feel free to download that under the same web page that you registered for this webinar. So now that the members are modeled, we need to also model our glass panel. And for this one, I'm just going to draw a general rectangular surface. And with the surface, so this is not going to be curved, it's just going to be in a single plane. We want to define here a new thickness type, just like with example number 1. We're going to select here the glass composition. And under the layers, so I mentioned taking advantage here of our library options. So defining these compositions, saving them to your library, because now for this example, I'm just going to choose a glass composition that I saved as a template. And you'll notice that all of the materials are brought in, the thicknesses, the edge finishing, all automatic. So I don't have to redefine those layers each time. Okay, so now that the thickness has been assigned here along with the material, what we will do is to snap from the upper left-hand corner to the lower right-hand corner to generate this surface. Now, in the current state, this is one continuous surface, and we certainly don't want that, right? We would rather infill each one of these bays that span in between the aluminum extrusions with a glass panel. So we have a nice modeling feature here where I can right click on this surface and I can go ahead and divide it by the intersecting lines. And so now what you'll notice is that I have individual glass surfaces here spanning between these aluminum extrusions. Now, going back to my folder here, Again, similar to example number 1, let us take a look at the glass compositions. So what the program does is it actually creates a separate composition for surfaces that share identical geometry. And this will come into play a little bit later on as we develop the insulated glass panel design. But for now, that's just why separate compositions are created here. So some of the compositions might have 2 surfaces, some might have 1, or some might even have 3. For all of these, I can just hold down my Shift key to select all of them. And for all the panels today, I want to change this to a rigid coupling. So I go ahead and make that composition change. I click OK, and now that's applied to all of my glass panels here. Now I'm going to select all of my surfaces, and we can double click on them. Again, exactly identical to example number 1. We have the strength and serviceability configurations. I'm not going to make any changes here. We're going to leave all of those as default to what we have already covered before. The only modification that I want to make here is I would like my reference length here to be the maximum boundary line for my glass panel for my deflection checks. And that's all that's required here for our glass input. Now, one thing to mention, these glass panels are rigidly connected to these aluminum members. If you have a scenario where maybe we want to account for some type of slip, or maybe we want to release the moment, depending how these glass panels are attaching to these aluminum members, we can always go under the option here, types for lines, and apply what we call a new line hinge. So if I double click on this, you'll notice that we have 3 degrees of translation, and then we also have our rotation. So we have the ability to completely release the moment, for example, of the glass panel to the aluminum member, or if we wanted to account for some type of slip again along the length of this connection, depending on our project type, we could input in here a spring constant. So that is always available again with these line hinges. Now for today, I'm just going to consider everything as a fully rigid connection between both the surfaces and the members. The final thing to talk about before we get into loading is just the aluminum members themselves. So I created here a couple visibilities where I want to look at first all of my members spanning in the global Y direction. So again, these are the members kind of spanning in between the vertical members here. Now for all of them, if we double click, we have the exact same concept for aluminum design as we do the glass design. And that's the benefit here of RFEM, is that these add-ons all have a very similar workflow and feel. So I am interested in carrying out the design according to the ADM. So I have my design property selected. Therefore, I have a couple additional tabs up here at the top that are specific to the ADM design. They do not affect the analysis. And the first one to talk about is effective lengths, or what are the unbraced lengths of these members. And I'll also preface that I did give a previous webinar devoted entirely to ADM member design, which I would refer you to, as we don't have much time to get into it today. But basically, we can turn on here the stability failure modes. And those include flexural buckling in the strong and weak axis direction. Now, this is a more box type section, so perhaps I'm not concerned with torsional buckling or lateral torsional buckling, so I can completely turn those off. But what the program does is we can place these intermediate supports at the member end. So these don't affect the analysis whatsoever. They're just used to automatically define the unbraced lengths. And in this case, it's set to the member start and member end. So the unbraced length is the full member length. But of course, we can make modifications here. So once we have input in the unbraced length, we also have strength and serviceability configurations for our aluminum design. And the strength I'll go ahead and leave as default, but for our serviceability, because these members are supporting these glass panels, they're probably a little bit, we need to have smaller limiting deflection ratios set here. So if we refer to something like the IBC, maybe we reduce the limiting deflection ratio for simply supported members to L/175 as well. So once this information is input for our transverse members, we also have our vertical members. And in this case, these were modeled as separate segments. So it's entirely possible, though, to design these as one continuous member. And how we do this is we can right click here under the member to create what we call member sets. Now, it's also possible to keep this as one continuous member. You don't have to break it apart. So both options are possible. But once we define those member sets, it's just grouping together these individual segments here for the member design. Again, so we can design it from top to bottom as one continuous member. But with member sets, it's the same workflow that we just saw with our members, where we would want to input in an effective length. And you can see for this one, a little bit more complicated because we have these various supports in the strong and weak axis direction framing into this member. But again, these are all used for the effective length in the strong and weak axis flexural buckling checks. Design configurations, we have already set these, so they're going to share the same configuration settings. And then the design support. So same thing for deflection. These members are supported sometimes in the weak axis, sometimes in the strong axis, just depending on the different members and support types in the global model. So we can also define here what we call design supports to be taken into consideration for those serviceability checks. Okay, so once we have input in this information specific to the ADM and our aluminum members, let's take a look here at the loading. And again, really identical workflow to example number 1. So we don't need to get into the same load combination generation, but I've created 5 different load cases here. The first 3 are going to be a dead load. And if I display the loads that have already been applied to this structure, you'll notice that if this is some type of facade, maybe we have some additional elements framing into it, and we have this downward load applied to each one of these transverse members. So this is just a simple member load where I applied it as 2 concentrated loads at 10% and then at 90% of the member length. The second dead load case is a really cool feature that we offer in RFEM. So under the load wizards, we have the option here to generate member loads from a free line load. And within this dialog box, we can specify here the load magnitude, the direction, which is in the global x-axis, and then the start node and end node. So that's what I went ahead and did here. I just defined this basic line load across the face of my facade wall. But I can right click here to display separately. And what the program does is it considers the tributary area of this line load and applies it automatically as point loads to each one of the relevant members in this vertical direction. So I use this for both load case number 2 and load case number 3. I just reversed the orientation here and adjusted the magnitude. Now we could always right click to display separately again if we'd like to see it as a continuous line load instead. For our wind pressure, we didn't previously have these surfaces modeled for our glass, so we need to quickly apply a new surface load here. And the load direction is going to be in the global X direction. The wind pressure here is going to be negative 0.015 under load case number 4, and we can select all of our surfaces, numbers 2 through 31. I click apply and next. We see that load applied here in the background. I'm going to change the load case to load case number 5 and just to simply adjust the magnitude here to 0.007 for my wind section. Again, selecting all of my surfaces. I click OK, and now we see that additional load applied here. And if we drop down to our load combinations, we can see all of these loads applied together on the structure. So the final thing to do before running our calculation is we want to jump down once again to the glass design add-on. And remember, we have these same design situations that we had in example number 1 with our ASD load combinations. We'll carry out the strength. Our IBC, we carry out the serviceability, and we're going to design all surfaces in the model. But we also have the aluminum design add-on as well. And you'll notice it's identical input here, that for our unfactored ASD load combinations, we will carry out the strength limit state design for ASD. Now, alternatively, if we were carrying out LRFD, we would probably want to enable this LRFD design situation here for that limit state type. I'll go ahead and use the IBC load combinations to carry out serviceability or deflection checks as well for my aluminum members. So when we're done with that, we can go to calculate all. Now the program will go ahead and generate our mesh for us. And we would want to ensure, just like with example number one, that that mesh was small enough. But what the program will then do is to run through each one of the load cases and the load combinations that we have defined here. So once we have the internal forces for our members from the various load combinations, we are going to bring them into the aluminum design add-on. And this is where we are going to apply, again, taking a step further from the static analysis to now the design according to the ADM, all of our design equations from the various chapters for both the members, and then you can see here it's now working on the member sets. So once this information is done for the aluminum design add-on, we take the results again from all of the load combinations here and we bring them into the glass design add-on to also carry out that design. So once this calculation is done, we are presented here with our results, and I will go ahead and drop down to the glass design add-on. So we can view the design ratios by surface, and we can filter here to any check that's greater than 0. And you'll notice that, very similar to example number one, we can view all of the information for the strength, principal, stress design in table format, as well as our deflection checks. And as we click on the table, we can see here it syncs up in the background to show us exactly which surface we're looking at, or I could graphically select my surface and we'll jump to the relevant design checks within the table. Turning back to the aluminum design add-on, again, same concept here, where we can view the design ratios according to the ADM, either by member, or maybe I want to take a look at the design ratios by member set. So remember that's these continuous members in the vertical direction. And you'll notice that for either the members or the member sets, we are carrying out every single design check within the ADM. So we see all chapters listed here and all relevant design check ratios. We can always filter here to the max controlling design ratio for each member as well. But the powerful thing that I mentioned of integrating that R section profile into RFEM are those local buckling checks. So you can see here local buckling according to chapter F. We can open up the design check details. And I could go ahead and zoom in here on my formulas to again see the references, the code references, all of the variables and input information line by line, and ultimately how we have determined this design check ratio for this member related to local buckling. We also can view the section classification. So here are all of those individual parts determined or set forth within our section. We refer to chapter V, B within the ADM to see how these are classified. We also can turn on here the diagram of the section, and maybe we drop down to the stresses and we can view any of the stresses on the element, including something like von Mises or shear stresses, to see the relevant stress under this particular loading. So serviceability checks are also available for either the members or the member set. So all in all, it's again very powerful that we can do the full design of the glass panels in addition to the supporting member design, whether it's aluminum, cold form steel, hot rolled steel, or whatever it may be. Now remember, we can always jump back to the static analysis results too to view this additional information for each one of the load combinations, including member internal forces or surfaces, surface stresses as well. Again, these are available under the various load combinations. Okay, so we will go back to our PowerPoint here to wrap up today's presentation. Just a few words on what we're currently working on for the Glass Design add-on. So as mentioned, we are currently in development with insulated glass design. This is something that we had in our older version, RFEM 5, but because we rewrote everything in RFEM 6 with better technology, better graphics, better workflows, this is taking just a little bit of time to get into the program. But once this is released, the powerful thing is that we will generate underneath the hood for something like insulated glass, a 3D FEA solid model. And this is again done all automatically within the program. And the reason why we have to do that is because we have to consider that nonlinear gas layer. What else is nice is that when we do release this solid model generation is that for either laminated or insulated glass, we can consider the true coupling behavior between the layers for shear. So we saw in the examples today, you can either set this to fully released or fully rigid, but with the 3D model, we can take into account the true stiffness behavior of those layers. We'll be able to soon apply climatic loads, again, important for those gas layers. And we're also working on additional international standards and implementing those within this add-on. So with that said, if anyone was interested in RFEM, you liked what you saw, maybe the glass design or any of our other capabilities, and you'd like to speak with someone on our sales team, feel free to reach out to us here. You can go ahead and access this request form through the QR code that comes directly to our website. Our information down at the bottom of the screen goes to our Philadelphia office as well. This PowerPoint is in the GoToWebinar, so you can go ahead and download that PDF to access all of this contact information here. So we will have many more upcoming webinars. You can register at deluwal.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these take place. So keep an eye out for the next webinar next month. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the states that we are pre-approved providers, that you're here for the full duration in order to receive that PDH. If you watched with a colleague or in a conference type setting and you yourself did not register for this webinar, but you were here for the full duration, go ahead and request that PDH to the email address shown here, info-us@deluwal.com. Again, if you yourself did not register and you are wanting PDH, let us know who you watched it with and we'll be happy to issue that PDH certificate as well. Just one more note about this, the PDH certificates are not instantaneously generated after the presentation ends. This usually takes us about a day or so before we will email those out. And with that said, I do want to thank everyone for attending today. There will be a short survey that pops up when you close out of the GoToWebinar. It would be great. You could help us out just filling out your feedback from today's presentation and help us improve in our webinars in the future. And with that said, thank you again, and I hope to see you at the next presentation. Thank you.